Here we're going to use Newton's laws to analyze what is known as an Atwood machine, which is really just two masses attached by a cord that are hanging over a pulley. So again, we have multiple objects, so we're going to have to draw a free body diagram of each object and then use them together to try to solve for what we're looking for. And what we're trying to find here is the acceleration of the blocks. Again, we're going to assume that they're attached by a rigid string, so the string can't stretch. The tension in the cable that they're attached by, and also we want to figure out what force does the pulley bracket, this thing up here, if this pulley was attached to something, what force does the pulley bracket feel? So for now, let's call this FB for the force on the pulley bracket. We'll call FT the tension in the cables. Now, one assumption we have to make is since they are rigid cables, that the tension in the cable over here is going to be the same as the tension in the cable over here because they can't stretch. They have to have the same tension on them. Now that we made our assumptions, let's draw some free body diagrams. We'll start with the red object. And again, really all of our forces are in the y direction this time, so our life's going to be a little bit easier. So the red object has a gravity force acting on it, and it has the tension in that string, applying an upward force on it. The blue object has a similar looking free body diagram. It has its own gravity force acting on it, and it has a tension acting on it upwards, and it's the same tension as the other one. Let's also draw a free body diagram of our bracket. I'll draw that down here. So our bracket has some upward force acting on it that we're trying to figure out. We'll call it FB. And it also has the strings. So it has two tension forces acting on it because each block is kind of pulling down on the bracket through the pulley that it's attached to. So we'll get to that one at the end. So now that we have these, we can just draw or write a couple Newton's second law equations based on our free body diagrams. Let's call up positive in this case. So we have for our red object, for object 1, we have a tension minus its weight equals its mass times acceleration in the y. Well, actually, we just put a because there was nothing really going on in the x direction. And for the blue objects, object number 2, we have that same tension minus its weight equals its mass times acceleration. Now, right now, we can't really solve either of these. Now, we can quickly find the weights. So we know the weight of the blue object. We're just going to do these quickly. We've done enough of these. Is just 3 times 10, which is 30 newtons. Again, we're assuming we're on Earth. And the red object is going to be 4 times 10, which is 14 newtons. So we know those. We can put those in, but we don't know the acceleration and we don't know the tension. So what ends up happening is that we cannot figure out what is going on here. We have too many variables. Now we could use our trick like we did before of 2 blocks and we could add these together, but there is a problem. Because of the way these things are moving, now originally I said I'm going to call up positive for the red object. Well, up being positive, the motion of the red object, if it's going up, that means the blue object is going down. So there's a weird little trick when you use pulleys, is that when you use pulleys, I know we always said you can never change your coordinate system once you pick it, but when we use pulleys, you sometimes have to, where the pulley actually what it does is it changes directions of motions of things. So what we're going to do is we're going to look at our system, make an assumption, or at least make a guess, and then we're going to rewrite our equations with a shifted coordinate system for each object. So the first thing I have to do is, just to make life easier, I want to try to make a guess. Which way is this thing going to go? Is the red object going to go down, or is the red object going to go up? Now, from experience and from common sense in life, I kind of know that the red object's heavier, so it's going to be the one that's falling down. So I'm going to actually change. Now I'm changing this, so I'm going to get rid of my equations that we wrote over here. I'm going to change for the red object, I'm going to call down positive because I know that's the direction it's going to move. And now if I kind of follow this back up and kind of like follow that arrow around the pulley over here on the blue object, that arrow would be pointing up. So for my blue object, I'm going to call up positive. Now I know this seems illegal, but because we're going through a pulley, pulleys, like I said, kind of change coordinate system directions. So really down for the red object or down for object one and up for object two are really the same direction because they move together that way. So now that I shifted that, let's rewrite our Newton's second law equations and see if they're any different or if maybe they can be solved easier. So we'll go back to the red object. We're going to have, now again, down's going to be positive. So we have the red object's weight minus the tension, because down is positive, equals the red object's mass times the acceleration. And for our blue object, we have tension is positive for our blue object because we're calling up positive. Actually, I called it FT. So let's use the correct variables that I have in my free body diagram. So FT is positive minus the weight of the blue object. And that equals the blue object's mass times the acceleration. And again, if you want to put mg instead of fg, that's fine too into your equations. But now, as I look at this, something nice is going to happen. If I look at these two equations, we did a little trick before. I'm going to add these. And notice what happens. If I add these two equations together, I get the Fr comes down, but here I have a minus tension, and down here I have a plus tension. They're going to cancel each other out. So the total ends up being FGR minus FGB, and that equals the masses are going to add together, mr plus mb times the acceleration. Now at this point, I can just put in numbers and I can solve for it, but I'm going to do one more little thing. We'll solve it algebraically first because we're going to see something nice comes out of it. Then we can put numbers in and get our answers. If I put FGR as mrg minus mbg equals mr plus mb times a, and then I pull the g out over here, I get mr minus mb times g equals mr plus mb times a. And if I solve for acceleration, it comes up in a really nice form that just says the acceleration is the ratio of the difference of the masses to the sum of the masses times whatever the gravity acceleration is. So in our case, this ends up being the difference of the masses is 4 minus 3. The sum of the masses is 4 plus 3 times our gravity acceleration, which is 10. And this gives us an acceleration of about 1.4 meters per second. So you get a really nice answer down here that tells you if you mess with if you change the masses of these two objects and you keep the total mass, the more different the masses are. The bigger the difference in the mass, the greater the acceleration you get. The closer they are, the less acceleration. If you distribute the mass equally, where they each get, in our case, 3.5 on each side, you would get no acceleration. They would just sit there balanced out. Now, the second part of our problem, it wants to know what is the tension in the cable. Well, now that we have the acceleration, we can go back and use either of our equations. Since I have some space where the red one is, let's use that one and plug in our numbers, and we can figure out what tension the cable feels. So let's see. The mass of the red object is 40, or the weight of the red object, rather, is 40, minus the tension in the cable, which is what we're looking for. That's going to equal the mass of the red object, which is 4, times our acceleration of 1.4. That tells us that the tension of the cable is going to be equal to 40 minus 4 times 1.4, which is about 34.4 newtons. And the last thing we want to do is, I'm not even going to write an equation for this because I'm running out of space, but also if we look at we want to figure out what force our bracket is feeling. Well, if we look at our equation, our free body diagram here, maybe I'll write a quick equation. The sum of the forces on it, again, the pulley bracket itself is not moving. So those forces are balanced out. It's just the bracket force minus double the tension equals 0. So the bracket is going to feel twice the tension, which is going to be about 68.8 newtons.